So we've seen this equation for kinetic energy before. Kinetic energy is 1/2 the mass times the velocity squared. The electron's energy and its position are complementary. The more we know about one, the less we know about the other. So for an electron with a particular energy, the best we can do is to describe its position in terms of an orbital, which is a probability distribution map. It's a three-dimensional probability map showing where the electron is likely to be found. The properties of atoms, many of them, are related to the energies of the electrons that are found in those atoms. So Schrödinger of Schrödinger's cat did some really seriously heavy math stuff. This is Schrödinger's equation, which I don't expect you to, I'm just like, oh yeah, I saw Schrödinger's equation. This is a wave function, and so this equation allows us to calculate probability of finding an electron. The solution to the equation produces wave functions that describe the wave-like nature of the electron. And if we plot the wave function squared, that represents an orbital. The size, shape, and orientation in space of that orbital are determined by 3 integer terms in that wave function. So there's 3 variables in the wave function that, depending on what value those have, it describes a different orbital. Those integers are called quantum numbers, and instead of A, B, and C, they are N, L, and M sub L. So the principal quantum number is N. We have the angular momentum quantum number, L, the magnetic quantum number, M sub L. And then there's a 4th quantum number that is the spin quantum number, M sub S, but that doesn't determine the size, shape, or orientation of an orbital. This is all going to just be a big muddle for a while, so just bear with me and hopefully we can put it all together at the end. So the principal quantum number determines the overall size and energy of an orbital, and this corresponds to Bohr's energy levels. So now you can see why Bohr's model of the atom is like kind of friendly seeming, right? It's like, okay, solar system, the electrons are orbiting the nucleus like the planets orbit the sun. I can understand that, right? Because planets are not quantum objects. So the principal quantum number corresponds to those different orbitals in those orbits in Bohr's model. So n can be 1, 2, 3, 4. The smallest value possible is 1, and then it goes up from there. It's an integer. An integer is a whole number, a counting number. 1, 2, 3, 4, 5. We can't have 1.5, right? Just integers. When n is larger, the orbital is larger in size and it's higher in energy. We can calculate this for hydrogen, and this is related to, blanking on his name. Yeah, I can't remember his name now. The guy that came up with the equation. Okay, you don't remember either, that's fine. So for hydrogen, we can calculate the energy of an electron that has a particular quantum number. It's minus 2.18 times 10 to the minus 18th joules times 1 over n squared. And again, n could be 1, 2, 3. So the energy there is negative. See, there's this negative sign? The energy is negative because the electron's energy is lowered by its interaction with the nucleus. Things tend to go towards lower energy. Balls roll down the hill. Going down the hill, you have less potential energy. Electrons go towards lower energy. So the electron is stabilized by its interaction with the nucleus. As n gets larger, the energy difference between the orbitals gets smaller. So we see that the orbitals get smaller. They get closer together. train. So here's an energy diagram for hydrogen. So if we look at energy going up on the screen, when n, that principal quantum number, equals 1, the energy of the electron is minus 28.18 times 10 to the minus 18 joules. When n equals 2, the energy is higher. It's less negative. And then for 3, it's getting smaller and smaller, less negative. Less negative is higher. And we see the distance between these two orbitals in energy, the difference is very large. The difference between 2 and 3 is smaller. Between 3 and 4 is smaller yet. And n equals 5 would probably be something like this. They just get closer and closer together in energy. The second number is L, the angular momentum quantum number, and this determines the shape of the orbital. So L can have integer values from 0 up to 1 less than whatever n is for that electron. And each value has a particular letter designation that we usually use instead of the actual numbers. And these letters are not something we made up just to make things difficult. The letters came first, and then the numbers came, and so people are just really hung up on the letters, and so we still have the letters. So if L equals 0, that's called S, and L equals 1 is P, L equals 2 is D, and L equals 3 is F. And you might think, well, why didn't they do A, B, C, D? Wouldn't that make more sense? Well, retrospectively, yes, it would. But these letters describe the lines that they saw in the emission spectra of elements. So there was sharp, principal, diffuse, and fine. And that's where those letters came from. I don't expect you to remember that, but there's a reason for them. Question?
Doesn't the orbitals, doesn't the periodic table, the way how it's shaped?
Yes. Yeah, we're going to see how quantum mechanics fits right into the shape of the periodic table, but not just yet. So what values of L are possible for something that has n equals 3? L can be 0 up until 1 less than 3. I mean, 1 less than n. Good grief. So what's 1 less than n? 2. So then it could be 0, 1, or 2, right? What? Are you seeing the problem I'm seeing here? Okay, I screwed up when I made the slide. What values of L are possible for n equals 3? So for n equals 3, L can equal, it starts at 0 and goes to 1, 2, we're going up to n minus 1. N minus 1, 3 minus 1 equals 2. Now, these numbers seem like they're just like super random and unrelated and stuff, and yet we have patterns of numbers like this in our everyday lives. So if we think about a date, right? Can you have May 35th? Why not? Because May only has 30 days. 31. Yeah, 31. It's a little song. Can we have September 31st? Yeah, think about that one. No, we can't, because September only has 30 days. Can we have October 31st? Yes. Well, that seems random. Well, yeah, it does seem random, right? And then there's February. Most years it's 28 days, but then every 4 years it's 29 days. But we seem to get along okay with that, right? These patterns are actually a lot more organized than that. Yes?
So if there will be n equals 3, can you have n equal 2 and would be 0, comma 1?
Yeah, so for this answer, that would be true if n equals 2. And this would be for n equals 1. And this one would be if n equals 4. Okay? The magnetic number specifies the orientation, the geometrical orientation in space, the direction in space. And these values can be positive or negative, including 0. So it goes from whatever L is, minus L, up to plus L, including 0. So as an example, when L equals 2, M sub L could be negative 2, negative 1, 0, positive 1, or positive 2. So M sub L is specifying the specific orbital. Hopefully I typed this one in correctly. What values of M sub L are possible for L equals 2? Well, M sub L goes from minus L up through 0 to positive L. So if L is 2, it's going to be D. L is 2, that minus 2, minus 1, 0, plus 1, plus 2. So this is L up to plus L. And then the spin quantum number. This gives the orientation of a particular electron. Electrons have spin. It's not clockwise or counterclockwise spin, but we can think of it that way, and that's good enough for Chem 1A. I don't know if you ever played Beyblade tops. You can get ones that spin clockwise and ones that spin counterclockwise, right? It's just a fundamental property of the top. And so here, the electrons have spin, and it's one way or the other way. And so that has the number plus 1/2 or minus 1/2. We tend to think of plus 1/2 is up and minus 1/2 is down. So to describe an orbital, we have a specific combination of 3 of the quantum numbers, n, L, and m sub L. So if n equals 1, L equals 0, and m sub L equals 0, this describes a 1s orbital. And if I want to look at a specific 2p orbital, it's going to have a different combination of quantum numbers. So each orbital has its unique set of quantum numbers, like each person has their own social security number, right? In theory, nobody else has it. They're not supposed to. If we have orbitals with the same value of n, these are in the same principal level, sometimes called a principal shell. And orbitals with the same values of n and L are said to be in the same sublevel. Okay, this is all really confusing, right? This is like making no sense at all, right? I completely am with you on that. Okay, I have an analogy coming up that will help us put this together. Okay, so don't fade away just yet. The number of sublevels in a level is equal to n. The number of orbitals within a sublevel is 2L plus 1, and the number of orbitals in a level is n squared. Okay, fine, whatever. What helps me to make sense of all of this is to think of this as a hotel, a really weird hotel. Can't remember where the slide is that actually gives that, but So this is like some weird inverted pyramid hotel. Maybe you'd find it in Vegas or something. Okay, so this is the first floor of the hotel, and this is the second floor, and this is the third floor. There's one room on the first floor, there's 2 rooms on the second floor, there's 3 rooms on the third floor. Guess how many rooms on the fourth floor? 4. That's okay, right? So the first room on any floor is called the S room. It's not room 1 or room 101, it's S. And this is on the first floor, and so this is 1S. On the second floor, it's 2S, and on the third floor, it's 3S. Normally in a hotel or any public building, the numbers of the rooms indicate what floor they are on. This room is 240. It's on the second floor, right? And hotels are like that too. You know, room 357, probably on the third floor, right? Well, instead of numbering the rooms like we do in buildings, they've got letter designations. So we've got S, and then if there's a second room, it's a P room. Here we've got the first one is S, and the second is P, and then D. On the fourth floor, there'd be S, P, D, and F. 4S, 4P, 4D, and 4F. Okay? So the floors of the hotel are the energy levels, the principal levels. These rooms are the sublevels, and then the actual orbitals are like the beds in the room. And so in this diagram, they're showing the orbitals, individual orbitals, as little squares. And so that's one bed. All of the S rooms have one bed. Why? Because that's how the hotel's set up. The P rooms all have 3 beds. Okay, a little weird. Even weirder, the D rooms have 5 beds. Have you ever seen a hotel room with 5 beds in it? Me neither. It would be great with my big family, but they don't make them like that. Guess how many rooms are in the F room? Beds are in the F room. 7. 1, 3, 5, 7. If there was another one, which there isn't, it'd be 9. Each of these orbitals can hold 2 electrons, but they have to have opposite spins in order to be in that orbital together. Yeah. Well, it's 2L plus 1, which is odd numbers. So here, this the number of orbitals in a sublevel, so that's the number of orbitals in this, or beds in this room. Here, L equals 2. So 2 times 2 is 4, plus 1 is 5. And so if we go to L equals 3, 3 times 2 plus 1 is 7. So in the hotel, each of these beds can hold 2 people, but they have to have opposite spins. Well, we'll figure out what that is in a minute. So we've got orbitals are the beds, the sublevels are the rooms, and the levels are the floors in the hotel. You see that there's like an actual pattern here that really is not stranger than everyday life kind of patterns that we know about. It's just that we can't see this structure of orbitals. You can't even, you can begin to generate computer images of it or something, but it's still just, it's hard. And so, but we can visualize a hotel, even a weird hotel. We can say, well, yeah, that's a really strange hotel. But you can imagine that and then remember stuff about it, right? So that's going to be good enough. The principal level is the value of the first quantum number, n. So that could be 1, 2, 3, 4, and that's the floor in the hotel.
That's the floor.
Yeah. So the set of quantum numbers describes where a particular electron is staying in the hotel. So if we've got an electron in this bed here, we could say, well, that's 3, 2, 0. third floor. L equals 2 is the P room, the D room, and 0 is that orbital in the middle with a particular orientation. It's a little bit like a VIN number on a car, where the first 2 digits give you the year, and then there's the day, the month, and the day, and then you've got the location and this thing and that thing, and it's all listed here. But there's only 4 numbers. List the quantum numbers associated with all of the 5D orbitals. How many 5D orbitals exist? So we've got N, we've got L, and we've got M sub L, and then there's M sub S. Those are the 4 quantum numbers. The principal quantum number is the main principal energy level in the hotel. It's the floor that room is on. Well, the 5D room, what floor is that on? The 5th floor. So that tells me that N equals 5. L tells me which room is it from the elevator. Is it the first one? That's the S room. Is it the second one? Is it the third one? So this is the 4th one, but the L numbers start at 0. 0, 1, 2, 3. So this would be L equals 3. L equals L. There's S, P, D, and F. It says L equals 0, 1, 2, and 3. It's not a 3, it's a 2. 0, 1, 2, S, P, D. It's the 3rd one in, but since it starts at 0, it's 2. And then what are the possible values for M sub L? Yeah, it goes from negative L up to positive L. So negative 2, negative 1, 0, 1, and 2. Mm-hmm. Well, this is the 1st, 2nd, 3rd, 4th.
It's the 3rd, that's where it is.
Yeah, so if I'm drawing the 5th floor of the hotel, right, there's the S room and the P room and the D room and the F room. But they're numbered 0, 1, 2, 3. Sorry, but they are.
So L was more, we're using the analogy for hotels, L was more horizontal and N is more
Yeah, you can think L is more vertical going up in the hotel, and then L is on that floor. How far away from the elevator are you? Yeah. And then in this room, so L equals 2, then we have a -2 orbital and a -1 orbital and a 0 orbital and a +1 orbital and a +2 orbital. And those are the beds in the room. And then electrons can have a spin, but this describes a specific electron in the orbitals. So here, make a new place. So if we want to look at the quantum numbers associated with this, so we've got one that's 5, 2, -2. 5, 2, -1, 5, 2, 0, 5, 2, +1, and 5, 2, +2. This is the first number.
Right.
They're all on the 5th floor, so they're all 5. This is the second number. They're all in that D room, and so L equals 2. And then the third number is different.
Oh, you're combining L and
I'm combining them, yes. This is N, L, M sub L.
Okay. That makes sense.
So it's a little bit like pinpointing a seat in the stadium, perhaps. You know, it's section H, row 5, seat 3, or something, right? And every seat in the stadium has its own description, its own unique description. So it's a different pattern, but it's the same idea.
So that's more MS, right?
Pardon me?
For MS.
So MS is going to be either plus 1/2 or minus 1/2. Because unlike seats in the stadium, these are beds in the hotel, and each bed can have 2 people in it, 2 electrons. The hotel is very strict. You can't sleep on the floor. You can't sleep in the bathtub. I don't know if you've ever been on a group outing, overnight trip, and there's like 4 guys that are assigned to this one hotel room, and there's 2 double beds. What usually happens is they fight for it, and 2 guys each take 1 bed, and the other 2 guys sleep on the floor, right? Because guys don't like to sleep with guys. Girls are a lot more okay with that. It's like, I'll stay on my side, you stay on your side. We're going to be comfortable. I'm not sleeping on that gross floor. And guys are like, I don't know, right? But in this hotel, the floor is lava. You cannot sleep on the floor. You just literally cannot. You have to share the bed with this other guy, right? So then what do? So here's the bed. They sleep opposite. So here's the bed. That's the headboard. This is a really crappy bed. So the one guy sleeps this way, and the other guy sleeps upside down.
That's for the spins.
Those are the spins.
Wait, so is MS always plus or minus 1/2?
Yes. MS is always plus 1/2 or minus 1/2. MS is you sleeping right side up in the bed, or you're upside down in the bed. And people actually used to do this. The soldiers at Fort Snelling, I know they slept in bunk beds, and they were narrower than twin beds, but 2 guys slept in one bed because it was freaking cold and they didn't have heaters, so they slept head to foot and kept each other warm, right? And you fit better that way than if you're going, next to each other. It's cold, yeah. So, analogies can only go so far. So I got to stretch it a little bit, but it's still a heck of a lot better than before I mentioned the hotel, isn't it? Yeah, okay. So the quantum numbers describe the particular locations. So each electron is going to have its own set of 4 quantum numbers. An orbital can have 2 electrons in it, and so in this orbital, we can have 2 electrons. So one would be 5, 2, 2 plus 1/2, and the other would be 5, 2, 2 minus 1/2. But every electron has its own set of numbers. Another practice question. Each set of quantum numbers is supposed to specify an orbital, but there's a mistake. Fix it. So here, n equals 3. Well, could n equal 3?
Can you go back real quick? I just
Yeah. Actually, I can't. I'm pretty sure I can't. I mean, I can do that. Oh, no, I can't. Sorry. It's gone. It'll be on YouTube later. So could n equal 3? Could there be a 3rd floor in the hotel? Sure. If we're on the 3rd floor, could we have a room that's L equals 3? No. Because there's 3 rooms on the 3rd floor, and they go 0, 1, 2. So this isn't possible. Now there's just 1 that we're supposed to fix. So this other one is plus 2. So that in an S room, you've just got 0, the one bed. In the P room, you've got -1, 0, and +1. In the D room, you have -2, -1, 0, +1, +2. So this must be the D room, right? In order to have an M sub L of +2. So L here has to be 2. For n equals 3, L could be 0 or 1, but if it was 0 or 1, then this number would be wrong also, and there can only be one wrong number because of how it's set up. Can n equal 2? Sure. If n equals 2, can L be 1? Mm-hmm. And if L is 1, can M sub L be -2? No. Because this is the second floor of the hotel. This is the P room. And we've got -1, 0, and +1. So this number is not possible. So you could put 3 different answers in here that would be correct. It'd be -1 or 0 or +1. Any of those would be correct. How about the last one? N can be 1. If n is 1, can L be 1? No. It goes 0, 1, 2, 3. Okay. So if n is 1, L has to be 0. If L is 0, can M sub L be 0? Yeah. Yeah.
If L was 0, would M sub L be -0 or +0 or be 0?
Just 0, because, yeah, -0 and +0 are the same as 0. It's a good question, though. I like that.
For M sub S, so it's always going to be +1/2?
Yeah, M sub S is either +1/2 or -1/2, and that doesn't depend on the orbital, the place where the electron is. It depends on the electron that's in the orbital.
So how do we determine that? Or we have to
Well,
draw diagrams?
We will have to draw some diagrams. The thing about the spin is that electrons can change their spin, and actually we don't really care what their spin is. It doesn't really come into anything that we deal with in 1A. And so basically what we do is we assume it's +1/2 for the first one and -1/2 for the second one. Like if you were sleeping in this weird hotel and you had the opportunity to choose which way you slept in the bed, I think most people would choose to sleep with their head at the top of the bed, right? And the next guy coming in has to be the awkward one. So that's what we do.
And then when we do this box right here,
Mm-hmm.
what were we setting as far as, I just missed that one.
These boxes?
No, this,
Oh, that was the quantum numbers, the sets of quantum numbers for those orbitals.
oh, okay, that's what we're doing.
Yeah. Yeah, okay. So now we can explain that atomic spectroscopy. When the light from an element lamp goes through a prism, we don't see a rainbow, we see a series of lines. Each line has its own wavelength, its own energy. So each of those wavelengths corresponds to an electron transition between orbitals. So when an atom absorbs energy, an electron gets excited to a higher energy orbital. Okay, so I didn't say what energy was in the hotel. What have I been likening energy to all semester? Money, right? So the energy is like money. These rooms have different rental rates, right? And so some of the rooms are cheaper and some of the rooms are more expensive. And electrons are cheap, like most people, and they want to stay in the cheapest room possible. So when the atom absorbs energy, the electron can go to a higher, more luxurious room, but it can't stay up there. It eventually moves back where it came from. And when it does, it emits energy. And that energy corresponds to the difference in energy between those two levels. That excited state is unstable, and the electron will relax to a lower energy orbital. It won't always go exactly back to where it came from, it'll go down. It may go down in a series of steps, but it will go down and eventually get to where it was. So the photon of light that gets released has the energy equal to the energy difference between the orbitals.
So it's like it's like light as a particle behavior, right?
It is like light as a particle, because when the electron goes down to a lower energy orbital, it emits a packet of light, a photon of light, a piece of light, a particle of light, however you want to describe it. So there's a picture. So if we're talking about this as being the hotel, here's the first floor and the second floor and the third floor. It costs more money to stay on the third floor. Now, if you need a reason, maybe the view out the window is better, I don't know. Or you're in less danger of being flooded, make something up. But the higher up you go, the more pricey the rooms are. So higher energy for higher floor in the hotel. So here's an electron that was staying on the first floor because he doesn't have a lot of money. But he got this windfall. I don't know, maybe he got, an inheritance, or he won at the slot machines. I somehow think that this hotel is in Las Vegas because it's so weird, right? And so he went out and played the slot machines and he won. And so he's going to blow his money on a night in this fancier room up on the third floor. So that's the money comes in and he goes up there, but then he can't sustain that. And so when he comes back down to a lower one, that difference comes out as energy. This is where haven't quite worked out the details of the analogy here. But when it comes down, a photon of light is emitted, and that photon of light has an energy that's equal to the energy difference in that transition that the electron's making.
So you can't stay on the third floor forever.
Can't stay on the third floor forever. It's not stable. We're really excited about it.
The bathroom's on the first floor.
Maybe. I have a lot of experience with teenage boys, and I'm now gaining more experience than I wanted with a teenage girl. Oh my. But my experience with teenage boys is they get up and they do stuff. Michael gets up and goes to football practice at 6 a.m. But does he maintain that level all day? No. He'll do that and then he's like back down. And what's the normal resting position? Flat in bed with the iPhone in front of you, right? Or asleep, right? So that's the normal position. He gets excited, he gets up, he does stuff, and then he comes back to his ground state. So that's what the electrons do. They'll go up, but then they come back down.
So it's just a fluctuation.
So fluctuation. The electrons go up in energy and back down in energy. And they can't just spontaneously go up. They have to get energy in to do that.
Where did you get that energy?
Excellent question. Where does the energy come from? The energy could come from light shining on them, because light is energy. It's going to come from an outside source. It could come from the element being heated. It could come from electrical energy. That's what's happening in those, like the hydrogen lamp. We're putting an electric voltage across and causing current to pass through, and that excites electrons, and then as they fall back down, they emit light, and that's what causes it to glow.
So anything that makes it excited.
Anything that puts energy into it. Yeah. So, in order to go to a higher energy state, it's not good enough to just get some money. You have to have the exact right amount of money, the exact amount of energy. It's like a bus where they just take exact change only. They won't let, it's like 75 cents, they won't let you pay $1. What's up with that? Why don't they want more money? You have to have exactly the right amount of energy to go up to that level. If you don't, you either stay where you are and the energy just goes past, or you find a different level to go to. But the energy coming in has to match just like the energy of the photon coming out matches, and that's why the absorption spectrum is the same. It's just that it's a dark spot instead of a bright spot. Electrons in higher energies are unstable and they lose energy and go down to lower energy states. So we can predict the spectrum of hydrogen. because Bohr's model works for hydrogen. It's just so much less complicated. The wavelengths of the lines in the emission spectrum of hydrogen can be predicted by calculating the difference in energy between two different states. For any energy state, there's n-1 energy states it can transition to, and so we can get n-1 lines. Very nice. I don't expect you to remember that. Both the Bohr model and quantum mechanical models predict the lines very well for a one-electron system. So the energy of the photon that's released, so the energy of the light that comes out, is the difference between the energy in the two levels. So the final minus the initial. So the final, the energy of the place it's going, minus the energy of the place it came from. And so we learned earlier that the energy of an electron in the orbital is minus 2.18 times 10 to the minus 8 joules times 1 over some number squared, an integer. So this is the energy of the final state. This is the energy of the initial state. We simplify that a little bit and we come up with this. So it's 1 over the final F squared, final N squared minus 1 over the initial N squared. And these are the sorts of calculations we were supposed to do in experiment 8A that we just kind of didn't do on Monday. The change in energy for the atom is opposite in sign to the change in energy for the photon. Because when the photon goes off with energy, the atom loses that energy. Yes? So what the heck am I doing? Is that what you're asking? Yeah. So E equals minus 2.18 times 10 to the minus 18 joules times 1 over N squared. That's the energy of an orbital for hydrogen. Not really. But that's where all of this mess is coming from. Is we're saying the final energy minus the initial energy. Well, the final energy is this equation where N is the final N. What floor did it go to? It went to the second floor. Okay, then N is 2. And we're going to subtract energy for the initial state. It came from the third floor, so then N is 3 here. But they both have this common factor in here, so we can factor that out and simplify it a little bit. So this has a very straightforward mathematical proof for the equation. I don't expect you to remember it or necessarily even understand it. It's okay. And the other thing is energy of the atom, change in energy of the atom is opposite to the change in energy of the photon. One's gaining and one's losing. And then remember that the wavelength is equal to hc over the energy. That's just a variation of the energy equals hc over lambda. So if we know the energy, we can calculate the wavelength of the light. So we're not going to do these calculations, but this is a diagram. So here are the principal energy levels for hydrogen, so like the floors of the hotel. And here we've got excited electrons that are going back down to lower floors. Well, this transition from 5 to 1, that's a big energy change. And so the photon that's given off there has a lot of energy, and it's actually in the ultraviolet region. And 4 to 1 and 3 to 1 and 2 to 1, those are all big energy changes. Those are in the ultraviolet region, the higher energy electromagnetic radiation we can't see with our eyes. These are the ones that we can see, from 5 to 2 and 4 to 2 and 3 to 2. The wavelength is related to the energy, and the energy is calculated by looking at initial N of 4 to a final N of 2, plug it into the equation, and it all comes out. And then these transitions also occur, but they are smaller in energy, and so those are in the infrared region, and we can't see those either. And then there's others, but again, they're outside of the visible region. Now, this kind of question could show up on an exam. Which transition emits light with the shortest wavelength? So what we need to remember is that as we're going up, they're getting closer together. Bless you. So going from the 3rd floor to the 4th floor is maybe $10 a night extra. But going from the 1st floor to the 2nd night is $40 a night extra. Right? So the difference is less as you go up and up. This is asking which transition emits the shortest wavelength. E equals hc over lambda, or lambda equals hc over E. If the energy is big, is the wavelength big or small? Small. So if I've got short wavelength, is this the one with the most energy change or the least energy change? The least, no, the most. Short wavelength, high energy. Okay, so short wavelength, so we're looking for the highest or largest energy change. Delta E. So before we start looking at these numbers, so here we've got 5 to 4, 4 to 3, 3 to 2. So they're not doing anything crazy and asking us to predict these 5 to 4, 4 to 3, 3 to 2. Which is a bigger energy change? 3 to 2. 2 to 1 would be even bigger. Because the energy is inversely proportional to the wavelength. So which of those waves looks more energetic? The bottom one, right? It's got a short wavelength. This one has a long wavelength. So 5 to 4 would have the longest wavelength, the lowest energy. And 3 to 2 of these choices is the highest energy, which is the shortest wavelength. And yes, it's very confusing. And that's why I don't recommend just trying to memorize stuff here. Because I don't. I think about it. And I think of this stupid picture in my head when I'm trying to figure out which is it. These are moving at the same speed. And it helps that this one looks more energetic, right?
High frequency, high energy.
High frequency, high energy, and that's short wavelength. So the shortest wavelength transition is going to be the one with the biggest energy change. Yeah. So these are the energy levels. So we were looking at transitions between n equals this, and this. This is n equals 1, n equals 2, etc. As you go higher in n, the difference between the levels gets smaller and smaller and smaller. Because I told you it does.
And the difference is equal to energy.
Yeah, so here, emitting light, you're emitting a photon of light whose energy is equal to the difference in energy between those two orbitals. So we only got 15 slides to go in, 6 minutes or something? We'll be fine. Be just fine. Determine the wavelength of the light absorbed when an electron in a hydrogen atom makes transition from an orbital in which n equals 2 to an orbital which n equals 7. So it's going from 2. So this is the initial is 2, and the final is 7. Now this here, the electron's going to a higher level, it's absorbing this energy. But the change in energy is going to be minus 2.18 times 10 to the minus 18. Oh, I'm blanking. Joules. Getting it mixed up with Planck's constant of the joule seconds. Times 1 over nf squared minus 1 over ni squared. If you get the final and the initial reversed, all that happens is the sign is opposite. And so you can actually fix that. Minus 2.18 times 10 to the minus 18 joules. The final is 7, so 7 squared minus 1 over 2 squared. So then, you have to get this on your calculator. Negative 2.18 EE minus 18 times, I'm going to use parentheses, 1 divided by 7 squared minus 1 divided by 2 squared, close the parentheses, 5.01 times 10 to the minus 19. That's the energy change. From the energy change, I can calculate the wavelength. The wavelength is hc over the energy change. So Planck's constant and the speed of light. And down here we have the energy, 5.01 times 10 to the minus 19 joules. So 6.626 EE minus 34 times 3 EE8 divided by 5.01 EE minus 19. So this is 3.97 times 10 to the minus 7 meters.
I was just going to ask that how did the sign change? But then the reason is because since the initial has a smaller number, it's
Yeah, this is going to be negative.
It's considered bigger.
Yeah. This is a change in energy here. A change in energy between those two levels. And so that's the energy of the photon that's absorbed or emitted.
So that's the equation of parentheses.
Well,
Which is the constant.
this is the equation to find the energy for the change.
Right.
So I solved that and I got this result. And that's the energy of the photon. And then I want the wavelength. So I have to use this equation to find the wavelength for that energy. Yeah.
HC is a given.
Yeah, this is E equals hc over lambda.
Speed of light.
H is Planck's constant, C is the speed of light. And this is an equation that was given earlier, and we've also seen it rearranged. So it's just an equation that is. Yeah. So I took this minus 2.18 times 10 to the minus 18th times the quantity, 1 over 49 minus 1 over 4.
I don't know, I'm getting 4.84 times 10 to the negative 20.
Yeah, so there's an issue with the calculator. We'll look at that outside of lecture. It's how you're talking to your calculator, and calculators need to be spoken to differently. They speak slightly different languages. And so, yeah, we'll have to look at that. The big idea here, because I think we're all lost in the details of all these letters and numbers, right? The big idea here is that for the hydrogen atom, we have this equation, and we can look at, okay, what two levels is the electron going between? We can calculate the energy. And we see that as the light given off or absorbed has a wavelength that corresponds to that energy. It's crazy. It's crazy. And we're like so out of time.